Here we go. All right, so welcome back. Got some homework. If anybody wants to go over any of those homework problems at all, questions about any of them?
Could you do number 18?
Number 18, that's on page 48.
Yeah, correct.
Number 18. Oh, that's the one with the ducks. Yeah. Lots of words on there, huh? All right. So first of all, they want you to change everything into statements. And like I keep repeating, that takes away a lot of confusion about words. And then we're just looking at sort of a structure here. And then, so let's change them into symbols here. Whoops. So there's what, 3 statements, okay? So was that, Robert, was that you that asked this question?
Yeah, that was me.
All right, so let's use your variables. What letters did you use?
I used for it walks like a duck as P, and talks like a duck as Q,
Okay.
and then it is a duck I thought would be R, but that's what was throwing me off. I didn't know if R had to be a thing.
Yeah, walks like a duck. And so there's 3, so these are called simple statements. They're just making one claim. When you throw in words like and or, that makes it something called a compound statement, just a combination of simple statements. So there's also walks like a duck, talks like a duck, and then is a duck as a statement. So you used are?
Yeah.
Okay. So are is a duck. Now, just to sort of away from your question here, sometimes it's nice to use letters that kind of make sense, although this is fine, but you might use W for walks like a duck.
Right. Okay.
But the 2 letters you should never use as a variable are T and F, because T is going to mean true. And so I wouldn't use T for talks like a duck, because T sounds like true, but you can use whatever letters you want. So let's look at the 3 statements here. So the first statement, I'll just say I, is if, so right away there's an if, so we know we have that arrow there. So if it walks like a duck and talks like a duck, so P and Q, whoops, then it is a duck. So there's that first statement. And the parentheses aren't really necessary here, but I think they help provide clarity to people who are reading it. And then we have the second statement, which is either it does not walk like a duck or does not talk like a duck, or it is a duck. So Robert, how did you do that one?
I had not P or not Q or R.
Okay, so not P or not Q or R. And that's a correct version of that. So that word either is almost extra. That sentence would still say the same thing with or without the word either or either, depending on how you say it. And then our third statement starts out with an if. So we know we have an if then statement. Does not walk like a duck and does not like a talk. So we have does not walk like a duck and does not talk like a duck. Then it's not a duck. All right. So there's the 3 statements converted into symbols. And there are different ways of writing it, but we'll go with this one here. And now the question is, are any of these statements equivalent? And whoops, hold on, I just lost the page. All right, so logically equivalent would mean you would go through these truth tables and they are exactly the same on every single row, then those 2 statements are equivalent, meaning they say the same thing in a slightly different way. So the truth tables on this are kind of a pain. Because you have 3 variables, P, Q, and R, your truth table is going to have 8 rows to it. So I don't know, did you happen to do any of those?
That's what was throwing me off. I didn't really know how to put that together.
Oh, okay. So it's going to take up a whole whiteboard. So you're going to have 8 rows. When you have 3 variables, each of which can be true or false, your truth table won't have 4 rows like we've been having. Your truth table is going to be 8 rows long, and then you go through and do all of that arithmetic.
Right. Okay.
All right. So I'm going to like back off from doing that. Right? It'll take us a long time.
Yeah.
You should do it though, but let's forget the truth tables. One of the things we want to get good at with logic is just by thinking about it critically, because nobody in real life in the middle of a courtroom trial, which is where logic gets used a lot, whips out paper and pencil and does truth tables. But just looking at these, do any of these seem like they would be saying the same thing? Did you like just thinking about the words?
The first two.
You think these two are the same?
Yeah, I agree. I think first 2.
Okay, so what you would want to do is set up the truth table, and that would conclusively prove or disprove your suspicions. So you're going to have P, Q, R. Oh, I don't even have enough room to do the truth tables here. So let me just get you started on the truth tables. So when you have 3 variables, your truth table will look like this: P, Q, R. And then you're going to have true, 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 false, true, false, true, true, false, 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 true, true, false, true, false. 1, 2, 3, 4, 5, 6, 7, and 8. So your truth table is going to have 8 rows. That's all possible combinations of true and false. And then over here, you'll have those 2 statements, and you just work out the arithmetic on that.
Right. Okay.
So is that enough to get you started?
Yeah, that's enough. I didn't know how to set that. I wasn't able to figure that out, but that helps.
Yeah, I mean, we could go through them here, but that would take up.
Yeah.
Say, truth tables are like they're kind of annoying, but they do remove any sort of emotional bias, if that makes any sense.
Mm-hmm.
If we had 4 variables, how many rows would we need? If you had P, Q, R, W or something, then how many rows?
Would that be 16?
Yep. So the number of rows is 2 to the power of the variables. So when we have P and Q, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32.
32, yeah. Okay.
Yeah. So yeah, so go through on those things.
Okay.
Just see what you come up with.
All right. Thank you very much.
Yeah. Okay. If any of you are familiar or somewhat competent with Microsoft Excel, Microsoft Excel does truth tables. It understands P's and Q's and ands and ors and those symbols, because essentially that's what's underneath running the program is all of this logic stuff. So if you're good with Microsoft Excel, you might want to experiment and see if you can get it to work out that way. Okay, questions on any of the other ones?
Remember 20F?
20F, oh, the one about something Tom and the cousin or something like that?
Yeah.
Yeah, hang on. I just lost the page. This the digital copy of this book is so sensitive to touch. So 20F. Okay, so 20F says write the negation of that. In other words, write a statement that would show that original statement to be false. So 20F. 20F says if, so if Tom is Ann's father, Tom is Ann's father, then Jim is her uncle. And okay, so there's the statement. Hang on just a second here. Hang on. Okay, so first of all, let's turn this into, and this is a good lead into what we're going to do today, by the way.
She didn't, the calls did.
What? What? Somebody have a question? Oh, okay. All right, so let's define some variables here. So let's make this. So let's make this P, Q, and R. Then this statement looks like this in symbols. There. So there's a statement. So Michaela, did you come up with words that would seem to make that false? What would have to happen for that not to be true? Did you come up with anything?
I just wasn't sure what's the negation of like if then.
Oh, well, let's look at that. All right. I'll show you what it is with a little bit of a truth table. All right.
Okay.
Well, first, let's look at this one. So if it is, and we're going to look at these statements today. That's what we're going to be doing today. If it is a dog, then it is a mammal. Is that the one I want to use? Hang on a minute. Yeah, why not? Well, yeah. Okay. Well, that statement's true, right? But we want to know what would have to happen if that was false. So if it is a dog, then it is a mammal. That would be false if you had a dog and it was
Not a mammal?
perfect. That's the negation of an if-then statement. So the negation of an if-then statement. The negation of an if-then, well, one of them, there's a couple of them, is this. So here's P, then Q. If I put it in front, we get the negation, and that's logically equivalent to P and not Q. So this is the negation of an if-then statement. If you have the if part, but you do not have the then part. So the conditional statement says this. We read this as if P then Q, but we can also say whenever you have this, you must have that. That's an if-then statement. Instead of the word if, we can use the statement whenever. Whenever it rains, there are clouds. If it rains, then there's clouds. That would be false if it was raining and there were no clouds. So the negation of 20F, so the negation, so this is 20F, that negation would be P and not Q and R. So that would say that Tom is Anne's father, and it's not true that Jim is the uncle and Sue is that. And using De Morgan's laws, we can multiply through by this not. So we could have P and not Q or not R. So the original statement, Tom is Anne's if Tom is Anne's father, then Jim is her uncle and Sue is her aunt, would be false if Tom is Anne's father and, or but, here's the word but replacing and again, Jim was not her uncle or Sue was not her aunt. So does that make sense?
Yes, thank you.
It does when you see it, doesn't it?
Yeah, like when you use it in words.
Yeah, well, sometimes words help, and sometimes words make it worse.
Yeah.
It's all very kind of frustrating, but hopefully at times when you're getting so frustrated, you're shaking your head, and then you just start laughing at yourself a little bit, right? Because these are simple English sentences, and yet suddenly we're thinking about what does that actually say? And we find that language is a very complicated thing, and we just don't think of it all the time, right? Like,
So I have a quick question for that. For this answer, I'm not sure if what I wrote is right because I can't really tell. I put Tom is Anne's father, and Jim is not her uncle, nor is Sue her aunt.
nor is correct.
Does that work? Okay.
Yeah, the word nor means not or. And I think, so neither nor, so there's either or, right? And then there's neither nor, which means not or. So you have a different version of this. And there is a symbol for nor, but we're using basic symbols here. For those of you in computer science programming, I think nor is one of the things that you have a character for, or something like that. So Nate, yeah, yours is fine. So you just wrote it in a slightly different style. It's all very confusing, isn't it? So, Michaela, I'm glad you asked that because we're going to look just at the conditional statement today. The conditional statement which is if, then, if P, then Q, whenever P, so the conditional statement is whenever you see this thing, you will always have that. That's when a conditional statement is true. But we're going to have a couple of manipulations of this. And I'm going to give names to these manipulations. And then your homework is just playing around with this. Because I think, in my experience anyhow, yours may vary, it's the rearrangement of the conditional statement can cause so much confusion because it can sound so reasonable, but yet it's not. So there's a couple of variations of this that we're going to look at. So for the conditional statement, we have the conditional, the contrapositive, positive, we have the converse, and we have the inverse. These are the four forms of the conditional statement. So, conditional statement is P then Q. So let me write the basic truth table down for that. True, true, false, false, true, false, true, false. So the conditional statement, P then Q, we went over this last time. This is only false one time. It is only false when the if part is true and the then part is false. It's true that it's raining, it's false that there's clouds. Well, that just can't happen. The conditional statement is true under every other possible outcome. And this is the strange one. This is true because it's not false, which is a different way of saying it. Now, if we look at the converse, the contrapositive. Contrapositive looks like this. So the contrapositive structurally is you swap places and you negate both of them. So if we go through this, so Q is true, This makes it false. P is true on the first line. That makes it false. And that is true, right? Looking at the basic truth table, false, false is true. So false, false is true. We go to the second row. P starts out true, but this makes it false. Q starts out false, this makes it true, and that gives us false. On the third row, Q is true, so that gives me false. P is false, that gives me true, that's true. And when they're both false down here, we get true and true. And we can see that the original statement and the contrapositive are identical in every line. That means these two are logically equivalent. They say exactly the same thing, just in a different way. So these two are equivalent. If it's a dog, then it's a mammal. So if dog, then mammal. If you flip it, if it's not a mammal, then it's not a dog. If it's raining, then there's clouds. If there's no clouds, then it's not raining. All right. So these two, and often when we go to prove stuff, when we start doing some like mathematical proofs, sometimes it's nicer to rearrange the statement here and work from there. So let's look at the converse. The converse, I'm running out of colors here. So the converse is switch them. Beginning with the initial conditional statement, if we flip them, let's see what's happening here. Well, everybody's true on the first row, so we get true, then true, which is true. So under the conditions, they're both true. The first row, they're the same under those conditions. Over here, if we flip them, we get false, then true, and that's true. And here, we see that they're different on the second row, just by swapping them around. And that, I don't have to do any more work on the truth table. From here, we can conclude that they are not equivalent. So if it's raining, then there's clouds. If you flip it, if there's clouds, then it's raining is not true. You can have clouds and no rain. If it's a dog, then it's a mammal. If you flip them, this says, if it's a mammal, then it must be a dog, and that's false. So the converse and the conditional, not equivalent. But sometimes it's easy to think that they might be. And if we look at the last one, the inverse, the form of the inverse is take the original conditional and just negate them. Not P, then not Q. We'll throw this. So here's an example of why truth tables are nice, even though they're tedious. So not P, then not Q. Well, let's just see. We can tell, I can give you an example to show that these two things are not the same. If it's raining, then there's clouds. This would say if it's not raining, then there's no clouds. Well, that doesn't have to be true. It can be not raining and have clouds. If it's a mammal, then it's a dog. This would say if it's not a mammal, then it can't be a dog. That's also false. So up here, we would get false, false, and that's true. So they're the same under the first conditions. And down here, we would get false, then true, which is also true. And we see again, on the second row, these two statements are different. So it's easy, sorry. It's easy though to have these statements be reasonable. Now, to say that the converse and the conditional are not logically equivalent, doesn't mean that sometimes they actually can turn out to be the same. Important to remember, in logic, when we say a statement is true, we mean that it's true every single time, no exceptions, not ever, not once. If we say a statement is false, the definition of false literally is just not true. A false statement can be true a gazillion times. It only has to be false once to declare that statement as a false statement. So it's easy to get caught up in things that sound reasonable. So conditional. Let me write a conditional statement this way. Here's what happens. I'm not using letters now, I'm using shapes. So the contrapositive, which we're going to use a lot, the contrapositive takes these two objects. I'm just going to use the word objects. Sometimes they're going to be English statements, sometimes they'll be math statements, sometimes they're going to be gibberish. But the if-then statement says, if this thing, then you will have this thing. So to do the contrapositive, you swap them, and then you put a not sign in front of them. And whatever this means, these two things have the same truth value under every single condition that there is. So the reason I use shapes is, if you look carefully, up here, look at the relationship between the converse and the inverse. What's the relationship between those two statements? Look carefully.
The same as between the conditional and contrapositive?
That's right. These two statements, I've taken the Q and P, flopped them and negated them. So the converse and the inverse
Oh, it's in the wrong window. Wait.
are contrapositives.
Dude, this shit is crazy.
It sure is. Are contrapositives of each other. Because they have this relationship on this structure. So the converse and the inverse always have the same truth value. The conditional and the contrapositive always have the same truth value, because this is a conditional statement. This says whenever you have Q, you're going to have P. So if you don't have the P, you can't have the Q. So they're contrapositives of each other. So this whole conditional thing, that's why in your book, there's an entire section devoted just to this statement. So if we look at some things, let's see here. So your homework tonight is just going to be fooling around with contrapositives and converse and all of that kind of thing. So let me give you a couple of examples. So this is the only thing we're doing today. It's going to be a short class because this is so important to everything else that's going to happen. I want to just focus on this today. So let's put an example here. If x squared is less than 4, then all right. Do we agree that statement's true? Not that it actually matters, but is that statement true?
Yes.
Yes. Didn't sound real confident there. Oh God, now it's algebra and numbers, right? Yeah, yeah, we all agree this is true, okay? Okay. What's the contrapositive of that? How do you can just say it in words. What's the contrapositive of that?
If,
Yeah,
if X is, oh, sorry.
go ahead.
If X is not between -2 and 2, then X squared is not less than 4.
All right. Everybody agree with that? Oh, 7th grade algebra, and you're all panicking, aren't you? That seem correct?
Yeah, I agree with that.
Okay. Now, let's use some De Morgan's laws. Let's rewrite this. If, get rid of the word not, and make this look just like algebra. Is this statement right here in parentheses, is this an and or an or statement?
And
It is. This says X is greater than -2 and less than 2. That's another word for between, isn't it? So we multiply through by the word not, the and changes to an or. And how do I rewrite this symbol? How do I rewrite that without a slash through it?
Greater than or equal to?
Greater than or equal to, that's good. Okay, so that's another way to write that. So we took the English word not, and we changed this and statement into an or statement. We could also do it with pictures if you have the number line and all of that. All right, now from the original statement, and by the way, these two statements are logically equivalent. They say exactly the same thing, just from a different perspective. So looking back, how do we write the converse here? If so we're doing the converse. Anybody want to be brave? Nobody can see you, by the way.
is it like if X is like in between -2 and 2, then X squared is less than 4?
That's correct. The converse is they just swap places. The word for that in arithmetic is commutative. So the converse is you just flip them, but don't do anything to them. Okay, so this is true. Well, let me do this. So this statement is true. This statement is true. Is that statement true?
No.
No, this statement is false. Now, it's possible the converse of a conditional can be true, but it's not guaranteed. So you've got to watch out for that. All right, and now let's do the inverse. So the inverse, if I know you're checking the structures on there. So what's the inverse going to give me?
If X squared is not less than 4, then X is not in between -2 and 2.
That's the correct statement. Ooh, that's a terrible looking then. And that's not much better. Okay, that's good. That's perfect. Is that true? And now you're thinking algebra, I can hear it. Is that true or false? So if we say, so x squared is greater than or equal to 4, that's another way of saying that, right? Maybe that's easier to look at. So if x squared is greater than or equal to 4, then that it must be true. So is that statement true or false?
I think it's true.
Think it's true?
Yeah.
So if x squared is greater than or equal to 4, then x can't be between -2 and 2.
Yeah, that's true.
Ah, okay. All right. Yeah. All right. So this converse, inverse, and all that, and I always get these mixed up. You know, right before class, I always get the converse, inverse structure. I don't know why it is. I always have to check to make sure which one it is. So it's not so much the names that are important, by the way. All right, so let's try another one of these. Pulling something up. All right, we'll take a simple statement here. So I'm saying if the object A is a square, then A is a rectangle, and that's true. What's the contrapositive of that? If
If it is not a rectangle, then object A is not a square.
If A is not a rectangle, then A is not square. And that statement is
True.
true. So if it's a square, then it's a rectangle. If it's raining, then there's clouds. If it's a dog, then it's a mammal. Every one of those things is the exact same structure. And now we go to the converse. So what's the converse of this?
If A is a rectangle, then A is a square.
Yeah, if A is a rectangle, then A is square. And that statement is,
False.
it could be true, right?
Yes.
It could be, but not guaranteed. So this is false. And then we go to the inverse. If
If A is not a square, then A is not a rectangle.
if A is not square, then A is not a rectangle. And that statement is
False.
but it could be true, right? But since we don't know without any other information, we cannot assume that that's true. If A is not a square, A could be a triangle, which would make it not a rectangle, but we don't know. So in the absence of other information, we have to declare that that statement is false. So it takes a little practice on these to kind of get good with them. And that's what your homework is going to be tonight, just this stuff here. So let me see what else we got. Let's see.
So I have a quick question. When you're saying for the converse and the inverse, when you're saying like that it could be true,
Right.
but is the converse always going to be false for the condition for any conditional statement?
No, it won't. So, and that's where things get confusing. So that's a really good question, by the way. So when we say, so the contrapositive and the conditional. These two things are equivalent. They will always have the same truth value. If this is true, this is true. If this is false, this is false. If this is false, this is false. If this is true, this is true. And then we have the converse and the inverse. Now, these are not equivalent, but that doesn't mean that they can sometimes be true. So for example, let me think of one here. Oh, if even, then, well, let me write this better. If n is even, then n is equal to 2k. Right, that's our definition of an even integer. If n is an even integer, then n is 2 times another integer. Now the converse of this, so what's the converse of this? If
n equals 2k, then n is an even integer.
Yep, then n is even. So these statements are both true, right? Here's the conditional. And the inverse of this, what's the inverse of this? If Heidi keeps falling out and coming back in. What's the inverse of this? If
n is not equal to 2k, then n is not an even integer. Oh, no.
not quite. If n
not even,
there you go. If n is not even,
then n is not equal to 2k.
Right, which is also true. And the contrapositive of this, is
If n is not equal to 2k, then n is not even.
correct. There we go. So all of these, they're all true. So here's a case where all 4 of them are true, but you can't, in general, because there are examples where these two are not the same as those, in general, they are not logically equivalent, except sometimes just by sometimes. To be logically equivalent means every single time you always have the same truth value. So here's a case where all of these are true. In fact, they're all true because I could write this a different way as an if and only if. N is even if and only if n is equal to 2k. So an if and only if statement is an if-then statement in both directions. So for if and only if statements, all 4 of these are always going to be true. Or they're always, all 4 of them will have the same truth values here. So it gets confusing, right? So you have to think and read very carefully. And again, you kind of have to think like a lawyer. You always got to be looking for loopholes. Let me see here. Hold on. Okay. So your homework tonight is going to be all about this and getting kind of used to all of that. On Thursday, we're going to begin to look at something called argument analysis, which is kind of where all this is leading. An argument mathematically is two or more statements, and we'll get into this next time, two or more statements that are called premises, followed by a single statement called a conclusion. And we're going to look at some of the rules to determine if an argument is valid, meaning does that conclusion correctly follow logically from the premises up above. The homework problems you did back in the beginning of the semester, wasn't all that long ago, figuring out where the treasure was, it was buried by the flagpole, who committed the crime. Those are all examples of arguments. And the conclusion is by the flagpole, or the conclusion was John did it. So police work is very much following premises, which are called clues and evidence, and come up with a conclusion of who did it, or this person definitely didn't do it. So homework tonight is just getting used to all of this kind of stuff, and it can be a little confusing, but you'll be much better for it after all of this. All right, so questions before we head off here? So you're going to get used to the words, keep those structures behind you. So here's what we have. So we have the conditional. We have the contrapositive. We have the converse. We have the inverse. All right, so the converse is you flip them, and the inverse is you negate them. And then we have the negation of. I should say a negation of. Now, there are other ways to negate an if-then, but this is pretty much the standard one. So you'll need these four things to work on the homework tonight. And there'll be a couple of other vocabulary words I'm going to throw at you in there as well.
Is that I think you may have written the inverse wrong.
Did I?
Maybe.
Did I? I did. See what I mean? I wrote it as the contrapositive. I don't know what it is. I always mess these two up. I never mess the contrapositive up, contrapositive. Those two I always mix up. Thank you, Nate, for catching that. I wrote that, didn't I? I don't know why I did that. Oh, I was looking at this, that's why. Okay, there we are. So these are correct. So that's what you'll need for tonight. Okay, anybody got questions or anything? Well, all right then. I'd say go outside and enjoy the day, but it's pretty chilly, but at least it's sunny. And I will see you back here on Thursday.